Lecorre. Mathieu es investigador de psicología de la Universidad Autónoma del Estado de Morelos. Y el título de su presentación es El origen de las representaciones mentales de los números naturales.
Buenas tardes. Rápidamente quiero agradecer a los organizadores por el congreso, está muy padre, gracias. Ok, pues ya saben el título de mi presentación. Eso es lo de... Yo odio hablar sentado, pero bueno. Eso es lo que les voy a decir hoy, de que les voy a hablar. Estoy supuesto a hablar en inglés. Ok, voy a pasar al inglés. Tengo todo en inglés en la cabeza. Perdón. Okay, so what I want to tell you about is, first I'm going to tell you about how children learn the meanings of number words and counting. And then I want to present the dominant interpretation of like what that means, what that process of acquisition means about the development of natural number concepts. This is a view that's been proposed by Susan Carey and Liz Spelke, that natural number concepts, I want to show you evidence that the concept of cardinality is available at least prior to the acquisition of counting, possibly prior to the acquisition of language. And I'm going to give you evidence for this from the acquisition of number words and counting in a sign language. Okay. Here's how children learn the meanings of number words and counting. Usually they start off by learning a small bit of the count list in their language. Say in Spanish they learn 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. They can say these words in order. And then later, the next step is they learn the meaning of one, or the meaning of the word for one, whatever it is in their language. And when they know the meaning of the word for one, they take all other words in their list to mean more than one. So, for example, if you ask a child at that stage to give you one fish, they'll give you one fish. And then if you ask that same child to give you 2 fish, they might give you 14 or 3 or 7. And same for if you ask them to give you 10 fish. So later on, kids go on to learn the meaning of the word 2, or the word for 2, then the word for 3, sometimes the word for 4, and only after they've learned each of these words one at a time do they learn the meaning of counting, namely that if I count the chairs over there, 1, 2, 3, 4, 5, 6, there's 6, right? Counting tells me which word to apply to the collection of chairs, for example. And so the crucial thing here to understand what's going on is, first you have to distinguish being able to recite the words in the right order from understanding what this act of counting actually means. So what goes on here, what I've described, is for a long time children would be or are able to count the chairs over there. 1, 2, 3, 4, 5, 6. But then you ask them how many there are, and their answer is not related to what they just counted. They might tell you 2, they might tell you 8, they might tell you 7. And this process lasts, I guess I should start with this point. This very, very sequence of acquisition has by now been observed in what is at least 9 languages in several different linguistic families. So this is how, this is the sequence children follow when they learn number words in English, in Spanish, in Russian, in Slovenian, in Mandarin, in Japanese, in Basque, in Tsamane, which is a language of a small indigenous group in Bolivia, and in the Najdi dialect of Arabic in Saudi Arabia. So this is very, very strong evidence that this process is the same regardless of the child's culture and the child's language. And what does, so the sequence doesn't change. What does change is how long it takes children to go through the process, to go from just having memorized the list and reciting it like a song to actually understanding what it means. So in very favorable conditions, it can take children 18 months, and in unfavorable conditions, it can take years. So children can be in a state where they know what 1 means, they know what 2 means, they can count to 10, but they have no idea what 3 means, no idea what 4 means, no idea what 5 means, no idea what 6 means. They can be in that state for months or years. Okay, so the question facing all cognitive, so now this is a really well-established phenomenon. It doesn't depend on who is testing the kids, it doesn't depend on where, it doesn't depend on the kids' parents. So really well-established phenomenon. You can go to a party, and if there's kids there between age 2 and age 5, probably you'll see, you test their knowledge of number words meanings, and you'll probably see all of these stages in the kids at the party. It's that reliable. So the question facing cognitive developmentalists is, why is this happening? Why is it like this? Well, the answer proposed by Susan Carey and Liz Spelke and many others is that, so, well, why is it like this? Well, the reason is that all humans interpret language with innate perceptual or cognitive primitives. And the innate primitives we have cannot represent the concepts that are expressed by number words in counting, namely natural number concepts. So that explains why the learning is so slow. The kids don't converge, take a very, very long time to converge on the adult meanings because they don't have the right kinds of concepts. They need to transform the concepts they have to be able to converge on the adult meanings. So the explanation here is what goes on when children are learning number words and learning the meaning of counting is that they construct natural number concepts for the first time in their personal life, not in the history of humanity, but so they construct natural number concepts for the first time when they learn how counting represents number. Okay, a note on, now I want to tell you more about what constructed means. It has very precise, rather precise meaning, and it's a negative definition really, is concepts are constructed if they can't be acquired by means of combinations of previously available concepts. So by combinations here I mean they can be propositional combinations or they can be associative combinations, it doesn't matter. Whichever of these kinds of combinations can't give you the new concepts. There has to be some other way of learning these concepts, and explaining what this other kind of way could be turns out to be extraordinarily difficult. Okay. So conceptual constructions in childhood often involve learning systems of concepts that were first created through the explicit efforts of multiple generations of thinkers. So many of these examples, unsurprisingly, come from concepts that were developed through science. So the distinction between heat and temperature, the Newtonian concepts of force and motion, imaginary numbers, all of these are cases that involve, when they're acquired by a human being, they receive these concepts from the culture, and they're acquired by a human being for the first time. Acquiring these concepts requires undergoing conceptual construction. And in development, as in history, the construction process is slow, piecemeal, and systematically distorted. So counting, the acquisition of the meaning of counting shows all of these features. So as predicted by the construction hypothesis, we see, I just showed you, that the learning of meanings of number words and counting is slow. It takes at least 18 months in the most favorable conditions on Earth. And in the least favorable conditions, it takes years. It's piecemeal in the sense that kids don't, they don't memorize the count list and then within a very short period understand what it means. Rather, they learn one. Then all they know is the meaning of, they have the word forms in their head. They know the word two, they know the word three, they just don't know what these things mean. And they're in that state for months or years. This is very, very, very different from the rest of language acquisition. Kids don't learn the word for chair. The time between the kids learn the form to refer to these things and the time when they learn its meaning is about 3 seconds. It's very, I mean, exaggerating, it's very, very fast. This is completely unlike typical word learning. And the process is systematically distorted in the sense that, like I've told you, when kids only know the meaning of one, they'll take two to apply to sets of 3, sets of 14, sets of 7. So this is not how the adults around them use the word two. I'll never say there's 2 chairs in the room, unless I'm being sort of like making sort of a pragmatic joke. Yeah, there are 2 chairs in the room because there are 54. So we don't use language that way. And yet, kids interpret the language that way systematically across the world. So this suggests that the cognitive apparatus they're using to interpret the language is systematically different from the cognitive apparatus, the concepts that adults are using. Okay, now I want to tell you that this is wrong. So the conclusion that's drawn from this is that, well, concepts for the natural numbers are constructed, they're not innate. And I want to tell you that that's, at least at the level of saying that, let's say a weaker interpretation is concepts of the natural numbers are not available prior to acquisition of language, and to have concepts of natural numbers, you need to learn counting. This is one I want to say is not true. I want to show you that actually concepts very close to the concepts of natural numbers are available prior to language acquisition and don't require the acquisition of counting. Okay, so what's wrong with this hypothesis? Well, the main assumption of an important assumption of the construction hypothesis is that when children learn how counting represents number, they learn how to represent the natural numbers as a possibly finite, non-looping sequence of objects. A simpler way to say this is that what kids are learning is that next in the count list means add 1. A more complicated way of saying this is that what kids are learning when they learn the meaning of counting is that they learn how counting implements the Peano-Dedekind axioms for the natural numbers, perhaps putting aside mathematical induction. Okay, here's the problem with this. This is not the only way of representing natural numbers. There is another way. And there's another way to think about what children learn when they learn the meaning of number words and what they learn when they learn the meaning of counting. And this is in terms of cardinality. What's cardinality? Well, in very simple terms, it's the answer to how many questions. So if I ask you how many A's are there in the word many, there's 1. Well, 1 is the cardinality of the collection of A's in the word many. Another way of saying what cardinality is that it organizes collections in equinumerous classes. And what it is for two classes to be, or two collections to be equinumerous is to be in one-to-one correspondence. So this row of chairs and the next row of chairs have the same cardinality because they are in one-to-one correspondence. Okay. Interesting, cardinality is really interesting concept or thing, depending on what kind of philosophy of mathematics you want to take. The only way to say what a particular cardinality is, not what cardinality in general, it's possible to say what cardinality in general is without referring to particular cardinalities. But if I want to say what a specific cardinality is, the only way for me to do it is to give an example of it. For example, 3 is the class of collections that are in one-to-one correspondence with the i's in that that I thing. There's no other way of saying what 3 is, unless I do it with the Peano-Dedekind axioms, and then we get in all kinds of interesting issues. But okay, so I propose that the content of the concept 3, there's probably multiple concepts of 3. It's something that Edouard Machery might like. The content of the concept 3 is something like in one-to-one correspondence with all other collections of 3. But as you immediately see, this can't be really right because it's hopelessly circular. To have the concept of 3, you need the concept of 3. That's just bizarre. But it's easy to break the circularity. The content of the concept 3 really is same number as some reference collection R. And the reference collection can be anything you like. And it doesn't have to be mental. It just needs, if it's going to work, if the reference collection is going to be useful, well, it needs to be easily accessible to users of the concept. So the reference collection can be body parts, skyscrapers, whatever. It doesn't matter. Blotches of blood, it doesn't matter. A very common, here's a very, very common way of building reference collections is to use verbal counting. So I think one of the meanings of, say, the word 27, when I say 27 Fs, what I'm saying is that the Fs are in one-to-one correspondence with the number words from 1 to 27. That's the meaning of 27. And this works obviously for all number words as long as they're part of the count list. Okay. All right. So now I want to say the concepts required to represent natural numbers qua finite cardinalities are not constructed, or at least they're not acquired when you learn verbal counting, and they're available prior to the acquisition of language for numbers. And also, what I'd like to say, if I had time, and probably won't, but is that what children learn when they learn the meaning of counting is just that a word n means in one-to-one correspondence with number words from 1 to n. They're not, when kids learn the meaning of counting, they're not learning that next means add 1. That's a slightly separate issue, although it's quite important in the end. Okay. So if I'm going to propose that the construction hypothesis is wrong, I owe you an account of why children learn number words and counting the way they do. And here's a hypothesis. It's easy for kids to learn one-to-one correspondence between words and objects, and we know this is true. Kids are able, when kids start counting, they spontaneously try to make their count match one-to-one with the objects they're counting. They do this kids do this at age 2. What's hard to learn here is that a single word, say 2 or 6, denotes a cardinality. Instead of, so what you have is the notion of one-to-one correspondence, and this disposes you to use reference collections as your symbols for natural numbers. Well, words like 2 or 6 are not reference collections. 2 doesn't have 2 parts, 6 doesn't have 6 parts. What does have 2 or 6 parts is a count to 2 or a count to 6. So what's hard for kids to learn, for example, in learning to count, is that 5, the word 5 by itself, can be used as an abbreviation of a count up to 5. That's the hard part. So if that's true, what I'm essentially telling you is that what's hard, what makes learning number word meanings and counting hard is that their form is arbitrary. The number words themselves cannot be used as reference collections because the number of parts they have doesn't correspond systematically to the number of things they refer to. So if that's true, then I could test this the following way. I look at number word learning in a language where word forms are in one-to-one correspondence with their reference. And luckily, there are languages like that, and they're sign languages. For example, the language I studied is Mexican Sign Language. I'll call it LSM for Lengua de Señas Mexicana. This is how the first 10, these are the signs for the first 10 numbers in Mexican Sign Language. So as you can see immediately, the signs for the number of extended fingers in the signs for 1 to 5 correspond one-to-one to the number they denote. And then starting at 6, that correspondence breaks. So at least by itself, the symbol for 6 is arbitrary. The fact that it's if you take it in the context of the whole symbol system, it's not arbitrary, but by itself it is. Okay. So if my hypothesis is right, that the concept of cardinality is available prior to language acquisition and prior to understanding counting, then the following should happen. Children should learn the meanings for 1 to 5 very fast, all at once, without distortions, and prior to understanding counting. And what I'm going to show you is that this is exactly what happens. Okay, I'm going to skip this. All right, here's the study I ran. My participants were 38 deaf kids, aged 3 to 9. Various kinds of exposure to LSM. The majority of them only had exposure to the language at school because their parents were not deaf and did not use a sign language at home. So this means for the kids at the bottom, these are unfavorable conditions for learning number words because the input they get is very limited. So yeah. If there's really a conceptual construction going on here, you'd expect that these kids who only get sign language at school will take years to learn the meanings of these words. And that's not what happens. Okay, I ran 2 tasks with these kids. One of them, I showed them some cards, and there's stickers on the cards, and they have to say how many stickers are on the card. And the other task is I gave the kids a bunch of poker chips, and they have to give me 1 or 3 or 6 or 10. And of course, I didn't run these tasks with the kids. I don't know LSM, so the experiments were administered by a Spanish, Mexican Sign Language bilingual person. Okay, so the crucial thing here is what do kids learn before they know the meaning of counting in Mexican Sign Language? So this is what I want to know. So what I did, I had this huge sample of 3-year-olds to 9-year-olds. I first determined which were the kids who understood counting, and then I saw whether in the rest of the kids, whether there's evidence of stages like you see in spoken languages, of where you learn 1, then 2, then 3, then 4, or whether it looks like the kids learn 1 to 5 all at once. Okay, so basically to be considered a kid who understood counting, you had to know, you had to show knowledge of the meanings of 1 through 5 on my tasks, and also of 6 and one higher number. And notice that the only way to get the meaning of 6 in Mexican Sign Language, or at least the most easiest way, is through counting. Because if you just match the fingers to object, you get the wrong numbers. This is not 1, it's 6. Okay, so the kids who could show me knowledge of the words at least up to 6 were kids who understood counting. Okay, now the question is, what's up with the rest of the kids? So I considered that the kids knew the meaning of a sign if they, this is data from the poker chip task where I asked them for a number, they have to give it to me. I said that you know the meaning of a certain sign, of a sign S, if and only if you give me the right number 2 times out of a maximum of 3 trials, and you never give me S objects when I ask you for other numbers, right? So basically, you know 3, if when I ask you for 3, you give me 3, and you never give me 3 when I ask you for other numbers. That's the criterion. Okay. So I found in my whole samples, I had, let's say, 11 counters. There's 9 real strong ones and 2 were borderline. And the kids that interest me is the kids that there's no chance that they understand counting. What do they know? I had 27 kids like this. These kids never use conventional counting when they're asked for 6 or more with conventional signs. And of course, the kids at the top often or always do. So they're very different in the strategies they use. Okay. This is what the distribution of kids looks like. So what the axis at the bottom tells you the highest number the highest number of poker chips the kids could give me correctly by the criterion I described. And what I see is that basically I have almost 90% of my kids by only taking into account kids who didn't know anything and kids who knew 1 through 5. There's nothing in between, almost nothing. This is absolutely not what happens in a spoken language. If you run this in a spoken language, you would see a whole bunch of kids who just know 1, a whole bunch of kids who know 1 and 2, a whole bunch of kids who know 1, 2, and 3, a few who know 1, 2, 3, 4, and 0 who know 1, 2, 3, 4, 5. There's been several studies of this, and kids who learn kids don't learn the meaning of 5 in a spoken language before they understand counting. So this is completely different. And it also suggests, since this is not, the ideal data would be longitudinal, where I see kids go, I have a little bit actually, I'll mention that very quickly. Anyway, there's the fact that we don't see, almost don't see any kids who know just 1 and 2, 1, 2, 3, blah, blah, blah. What we mostly see is basically kids who know nothing and kids who know 1 through 5 suggest that kids in a sign language learn 1 through 5 all at once. And I actually have longitudinal data on one kid who, when I first observed him, he didn't know anything. Then I saw him 3 months later and he knew 1 through 5. Here's what interesting things that these kids who know up to 5 do when they did the card task. They actually, so this is not the sign for 6 in Mexican language. This is in Mexican Sign Language. But the kids, when we tested them, had created signs for numbers larger than 5 that are not the signs that are used conventionally in Mexican Sign Language. Maybe they learned these at home, but the point is they're able they're even able to understand signs for number larger than 5, and the way they do it is by using 1-to-1 correspondence. So here's a little girl signing 6 in 2 different ways in the same session. At the top she signs 6 this way and it's correct. There are 6 things on the card, and later in the session she signs 6 this way. None of the teachers at her school do it that way. And here's a little girl signing 10 with 2 hands. This is not the sign in Mexican sign for 10 in Mexican Sign Language. This is the sign for 10. So, I want to suggest, based on these data, that the concepts required to represent natural numbers qua finite cardinalities are not constructed, or at least they're not acquired when you learn verbal counting, and they're available prior to the acquisition of language for numbers. Thank you.
Thank you. Tenemos tiempo para preguntas.
Tengo dos comentarios. Podría ser discutible si cuentan o no para aprender el símbolo en el lenguaje de señas mexicano.
¿Si cuentan o no?
Sí.
Tengo evidencia que no cuentan.
Bueno, pues te concedo que no. Supongamos que concedemos ese punto, no es importante. Porque lo importante es que lo que parece derivarse es que, igual que los hablantes, los sordos también necesitan primero el símbolo para captar el número, el concepto del número. Necesitan el símbolo.
¿Cómo sabemos eso? ¿Cómo interpretan los símbolos si no tienen conceptos para interpretarlos? Esa es la pregunta. No se interpreta un símbolo de la nada.
Porque han aprendido el símbolo. Igual que en el lenguaje oral, primero tienen que aprender la forma del numeral, la palabra del número, y luego asociarla al concepto que expresa, pues aquí también tienen que hacer eso. Y claro, en la medida que aprenden digamos, el significado del gesto, captan el número. Esta sería una consideración. La otra es que en la caracterización sobre todo de Spelke, uno podría decir que no has tenido en cuenta o no has presentado que en la idea esta del core knowledge, del conocimiento matemático, sí conceden que hay una disposición inicial para la cardinalidad.
Pero no es la que propongo. Ella misma.
Y para la numerosidad.
Ella misma está sorprendida de esos datos y está de acuerdo que son un problema para su teoría.
Hay más preguntas, dos más.
Yeah.
Es para la grabación del vídeo.
Good, so I won't scream. So 2 questions. The first one is more theoretical. So the account of content for number concepts you give us can't really be true of all number concepts. Think, for example, about 1027. I don't have a reference. It's a number concept. The concept of 1027.
Okay, you're just making up that word.
Of course, I'm just take a random number.
Okay.
I don't have a reference class for that number. I may have a reference class for 1, 2, 3, 4, 5.
No, you do. If you can count to 1027, you have a reference class for it.
Okay. And I don't have one in my head just now, right? And nonetheless, I understand. So. And so that's related to something that can, even on your peak, I think, very convincing data, so people do seem to have an understanding of some number concepts before being able to count. On the other hand, there's still room for learning something while counting, which is a successor notion. Right?
Absolutely.
And so you could have, combine your data with the idea, well, by counting you acquire the concept of succession.
It turns out that that's not what kids learn when they learn the meaning of counting, but...
Right, but it still needs to come from somewhere, right?
Absolutely.
You still need to understand succession from somewhere.
The only claim I want to make here is, suppose we grant that, I think this is fine mathematically, finite cardinalities are natural numbers. Natural numbers and cardinalities become different when you start talking about infinite cardinalities. But, what the claim that is changed by these data is that there are no concepts for natural numbers prior to the action.
I agree. And just a quick experimental question about the data. Is there a sign language where you have a different system of signs that would give you a very nice control for the Mexican data? So if you could find, for example, if in ALS, it's not 1, 2, 3, 4, 5,
Yeah.
but it's artificial number, just like 1, 2, 3, 4, 5.
Uh-huh.
It would be very nice to show that you get only this bimodal distribution when you have
That's cool.
the reference class given.
That's very cool, yeah.
And so I don't really know whether you...
Me neither, but I'll look it up.
Yeah, that would be a very nice control.
Yeah, cool, thanks.
Okay. Otra pregunta aquí.
Gracias. Bueno, mi pregunta va en dirección de que para el concepto de número tal vez sea necesario la ayuda de los símbolos más que de las palabras para que nos ayuden a tener el número abstracto. Para poder acceder a lo que es un número abstracto, creo que es necesaria la ayuda de los símbolos.
¿Por qué?
Porque cuando en los lenguajes primitivos siempre la palabra para 3 casas o 3 caballos estaba asociada, había una palabra diferente para 3 caballos que para 3 árboles, para 3 Cuando se unifican los símbolos, por ahí en Sumeria, por ahí 3000 años antes de Cristo, por ahí cuando se unifican los símbolos, entonces tenemos un solo símbolo para 3 casas, 3 caballos, etc.
La pregunta que tendría para usted es que, ¿qué hay aquí que no sea abstracto? La noción de correspondencia 1 por 1 es abstracta. Porque involucra, involucra el cuantificador universal, cada, y involucra la noción de unidad.
No, bueno, para hacer la relación 1 a 1, de hecho, eso le suelen llamar contar sin números, porque podemos agarrar piedritas.
Pero yo
incluso,
creo que siempre contamos sin números.
Bueno,
porque contar es hacer exactamente eso.
Eso, bueno, no
533, estoy de acuerdo con la observación de Eduard, que hay otra parte del significado de número que no tiene que ver con eso. Pero lo que me dice que 527 es 527, es que, pues, 527 es... las cosas tienen 527 si están en correspondencia 1 por 1 con un conteo de 1 a 527. La parte donde estoy de acuerdo con usted es hay una abstracción que sucede cuando el concepto, cuando la forma del concepto ya no tiene ninguna característica de su referente. Por ejemplo, 5 no tiene ninguna característica de su referente. Pero 1, 2, 3, 4, 5 sí tiene una característica de sus referentes, o sea, que se puede poner en correspondencia 1 por 1. Y parece que eso de adquirir, de ser capaz de manejar símbolos que no tienen ninguna característica numérica en sí, que no son un conjunto de objetos, eso es difícil para los niños. Y a lo mejor es un paso importante en las matemáticas, por ejemplo, porque son símbolos más manipulables, como no creo que es no es una diferencia de contenido, es una diferencia de manipulidad, como para crear nuevos símbolos como -5 o raíz cuadrada de -1, es más fácil hacerlo con símbolos que no tienen ninguna característica de sus referentes que con colecciones de objetos. Pero lo que le pediría es que me clarifique esa noción de abstracción.
Bueno, porque a mí me llamó la atención cuando dijo...
Pero a lo mejor durante el café.
Que ahorita a lo mejor, sí.
Sí.
Ok. Bueno, ok.
Última pregunta.
Sí, gracias. La primera cosa es un comentario, que el estudio parece ser más sobre cantidades prototípicas de poco tamaño, más que números naturales. Los números naturales es una abstracción matemática axiomatizada por Peano, o sea, hay números que ni tú, ni yo, ni nadie los ha pensado, ni nadie los pensará, y que son números naturales, y son infinitos. Por lo tanto, el número 3.494.323 es tan natural como el 2.
Sí.
Entonces, al hacer el estudio con 1, 2, 3, 4, 5, básicamente es un estudio de de las cantidades prototípicas de conteo, más que de números naturales propiamente tal.
¿Qué hay de, no entiendo qué es una cantidad prototípica?
Una cantidad prototípica son esas que manejamos habitualmente, vale decir, si yo te digo a ti, piensa en un número del 1 al 10 y si le chuntas te regalo una cerveza.
Pero
Bueno,
mira,
lo prototípico sería decir un número entero, pero si mi número es...
dos respuestas. La pregunta es,
No te ganan la cerveza.
¿qué son los conceptos que permiten a los niños interpretar esos símbolos con tanta facilidad y crear nuevos? Que van más allá del 5,
Sí,
si no
está
son
bien,
parte
está
de...
bien. Lo que quería decir simplemente que el estudio, como dice el título, no parece ser tanto los números naturales, sino como la...
Pero el problema es que Gottlob Frege estaría en desacuerdo contigo.
¿Quién?
Gottlob Frege.
Ah, pero claro, estaríamos diciendo muchas más cosas, pero...
Pero es
punto acá de lo
importante,
natural.
es decir, es desacuerdo no porque se despertó en la mañana y no le gustaba la idea, es que se mostró que se puede derivar lógicamente la noción de número natural abstracta, tal que es la que indicas, a partir de los conceptos que manejan los niños ahí, a lo mejor. Entonces, la objeción no me parece válida.
No es una objeción, es un comentario.
Pues el comentario no me parece válido.
Que me parece que es un subconjunto de los números naturales, que son aquellos que usamos casi todos los
Pero
días.
para mostrar que los niños tienen concepto de números naturales, ¿tendría que probarlos todos?
Es que ahí
es
ahí
un
donde
experimento imposible.
ahí donde empieza a correr más la observación de la sucesión, que son otras propiedades distintas. Y esto me lleva a la pregunta que te quiero hacer. Parece ser que cuando dice el concepto de 5 o 4, es como si fuese monolítico. Pero yo puedo tener un concepto de 6 que es basado por ejemplo, en 3 pares. Y lo que cuento son pares o tríos. Y ese es mi concepto. Y en ese sentido distinto que es el número que sigue al 5.
Sí, eso me parece una distinción que no hace una diferencia.
La hace porque es polisémica, entonces en el fondo es una diferente forma de poder concebir un concepto que no es monolítico, sino que puede tener la extensionalidad.
Sí, estoy de acuerdo que justamente como lo concebí, pues creo que es cierto que tenemos múltiples representaciones de números. Por ejemplo, la representación análoga, el ANS, Approximate Number System, funciona de manera totalmente diferente. Pero este es una caracterización de a lo mejor uno de los varios conceptos de número que tenemos. Y en cuanto a esto, mi representación, que no tiene que ser mental, mi símbolo para 6 o 5, que sea en este contexto, que sea un par y un trío o 5, no entiendo la diferencia.
Bueno, tal vez podemos continuar durante la pausa y muchas gracias, Mathieu.